Riley, and it's a big if you watch this video, I forgot to record while I was talking about what all this stuff is. Hopefully you can figure it out. Sorry. Anyways, here's one's not about that, but the first derivative rule still applies. Find the rate of change of the circle's area with respect to its radius and r equals 3 and r equals 6. Now, to do this problem, really all you have to know is the form of area of the circle. How do you find the area of the circle? R squared. Well, we're just going to take its derivative, the rate of change with respect to area. I'm going to find a prime in that circle. And yeah, there's a pi symbol, but that's still the easy rule, isn't it? Where does the 2 go? Up front. We're not doing the product rule. Pi is just a number. If it was a 3, we wouldn't worry about it. Don't want to get here. And we decrease the exponent r by 1, so now it's just r. Oddly enough, the change in a circle's area with respect to its radius turns out to be 100%. There's nothing special about that. It's just the way it is. Okay. Not going to give you the negative right. So don't overthink it that it's even special. Because it's not. Well, what they're asking us to do is they're kind of trying to say, hey, does area grow faster with a smaller radius than it does with a bigger radius? You can kind of see that. Plug numbers in. We'll find a prime of 3 by plugging in 3. Twice pi times 3. I guess that's what, 6 pi? So at the moment a circle, and just imagine, this is an oil spill or something like that. You ever like change oil in your car and something comes out, you can't find it. Color grows bigger and bigger and bigger. So when the radius is 3, at that moment in time, the area of that oil spill is growing at a rate of 3 pi, it could be inches per second, minute, whatever, however fast it's happening. Now at 6, the radius is much bigger. You would expect area to be growing quicker. And it is. Growing a lot quicker. Because it's a circle. It goes back to the circle's formula for area. Bigger radius, bigger area. Assuming that the radius is growing at the same rate in both instances. The area of the circle is growing faster. So there's some context issues there that can be a little bit confusing, but don't. Just trust the numbers, and as you get older, if you keep studying math, it'll click. A lot of math is interesting. You don't really understand the course you had until you take the course after. Like if there was an Algebra 3, you would completely understand Algebra 2 about halfway through Algebra 3. That's just how it is. The same way with Calc. You really don't, Calc 1 doesn't really click until about halfway through Calc 2. I noticed that growing up because honestly, we move a lot of times at too fast a pace for you to really retain things. So not really until the next course that you understand the previous course. All right, here we go. Using positions to determine velocity. Oh, this is about a failing kid. Failing kid is launched from a catapult. A function modeling his or her height as a function of time is h of t equals negative 16t squared plus 200t plus 12. I don't think you probably remember these, but this first piece is the pull of gravity on Earth in free fall. So it assumes no resistance. This is the initial acceleration. It's launched at 200 feet per second. And that's the initial height from being launched. Now our task here is to find the student's velocity at t equals 2 and t equals 4. It doesn't say find height, does it? That's the function model's height. This says find velocity. So that's kind of the reason I gave you those notes on the first page. Velocity is what derivative? First. Velocity is first derivative. See the word velocity, you find first derivative. In this case, h prime. Well, that's an easy one to do. What's the derivative of negative 16t squared? Negative 32t. Derivative 200t. It's 200. Then derivative 12 is 0. Now, That negative 32 is the rate that the Earth pulls an object down by gravity. The Earth pulls anything down at 32 feet per second. That's why it's shown up there, okay? Just physics kids. You know, because when I was in the algorithm, all of that sort of right, which inspired me to create calculus. Whatever. How it inspired me to create calculus. So we're going to find h prime of 2. We're going to plug in 2. That's a negative 64 and 200, which is what, 146, 136. Units here would be feet per second. You understand the units why I wrote feet per second? I didn't write down our actual function, but time here is long in seconds, not minutes or hours. Could you imagine a 2-hour catapult ride? It's in seconds. And the function, when I was talking about it, 200 feet per second is acceleration, so this is feet per second. What's going to happen at 4 seconds? Is it going to be moving faster or slower? It's going to be moving slower. There's a good reason for that. What, negative 128 and 200, so 72. If you were actually look at this function, it's just a parabola, isn't it? You got out your TI-84, did it by hand. It looks something like this. That's about what it would look like. So at 2 seconds, the function, the kid's height is about right there. But at 4 seconds, he's getting really close to the top. What's happening to the slope of that parabola at the top? It's flattening out because gravity is about to win. That's why the speed is slowing down. Okay? And he's going to go over the top, and gravity's going to start feeding the speed back. And he's going to die. Because he's going to hit the ground at a very fast rate of speed. And there's nothing anybody can do about it. Except study harder. It's a joke, but could you imagine, like, if we took the worst kid in public high school every year and just executed them in a front yard? How great academics would become in just a short order of time. You voted red, didn't you? That's the truth, probably, on that one. And what's saying is there'd be a lot of red kids we'd be taking out there. It's just funny stuff, kids. I don't mean it. I'd never do it. You think I'd kill somebody?
It depends on the situation.
If they broke into my house, I would. Wouldn't think twice of it. You wouldn't? I would.
I'm kind of weak.
That's what guns are for. If you think that's wrong, don't become a husband. Because that's part of the title. Defend. What velocity will a student be traveling when they go splat? Ooh, this is the interesting part. All right, first we got to figure out how long it takes them to go splat, right? Do you want to do that by hand? I don't either. Do you remember how we might do it with the technology? Maybe go to good old y equals. But you go splat when your height is what? 0. That's when you go splat. I can't remember if I taught you guys to use the 0 function or if I taught you to use the intersect feature. Probably taught you all to use the intersect feature. You don't have to put anything into y2. I'm not going to. I really don't care to see the entire parabola. Zoom 6 will probably cover it. He's only going up 200 feet per second. I guess the Zoom 6 doesn't cover it. So he's probably going to go splat somewhere off to the right, don't you think? I don't know. Make X max 20. There's splat. You guys are smart enough to realize that this thing went up and then it came down. You don't need to see the whole thing. I don't think I showed you this in Algebra 2. I'm going to do a second calc 2, 0. That's the goal, right? Find out when y is 0. And once you do second trace 2, you'll see it asks for left boundary. Now here's the only problem with using the 0 function. You have to realize that the top, right here above the axis, x-axis right here, that is left of where you cross the x-axis. And down here, after you cross the x-axis, would be to the right. Not every kid sees that. Some kids just see a vertical line and left and right don't make sense to them. That's probably why I showed you all the intersect feature. But I'm going to take my little cursor. You got to be on the hunt for it and pay attention to what it says x and y are. And I'm going to get it to the left of the x-axis. Like, look what happened. It wasn't even visible, was it? But where y is 43 would be somewhere over here, left of that 0. So I'm going to press enter. Then it's asking for a right boundary, so I'm going to press the right button. Now y is negative 20. I know that's down here somewhere on the right of that 0. Press enter. Enter for a guess. And the kid has roughly 12.5 seconds of life. Now, thing like that, the way I did that with 0 function, you can always put a 0 into y2 and there's an intersect feature. It still works. It always works. The time is about 12.56 seconds. Time of death, 12.56 seconds. I want to know at what velocity they're moving. So I plug that into h prime, right? H prime 12.56. And 32 times 12.56 plus 200. Negative 201.92 feet per second. How fast that is in miles per hour. That's per second. How many seconds in a minute? That's feet per minute. Right? Minutes an hour. That's feet per hour. How many feet a mile? Divided by 5280. That's how fast a kid hits the ground. Not at negative 137 miles per hour. It's negative because he's going down. Okay? The kid hits the ground at 137 miles per hour. Dead. Dead. The whole point of using death as an example is try to make it a little bit interesting. It's the whole reason. Just make it a little bit interesting. I'm not going to build a catapult and launch one of you from it. But if we did, we'd sell tickets. We would make it a fundraiser. People would show up for that all day long. All right, this is interpretation of a velocity graph. It's really not. I'll try not to use math notation for you. All right, so from time equals 0 to time equals 1. This is the time axis. It's dot velocity, right? That's time. And going up is your velocity. From Time is 0 to 1. What's happening to the velocity? It's increasing. Another big deal here. Positive. This is implying movement up or maybe movement right or something. Okay. It's positive. It's positive because it's in the above the x-axis. It's a big deal. From time equals 1 to time equals 2. What can you tell me about the velocity? It's constant. There is you know, the velocity is constant. Your speed in this case. All right. That's probably about 3.5. That's what I'm going to call it. From t equals 2 to t equals 3.5. What can you tell me about the velocity? It's decreasing, but it's still positive. Why am I saying it's still positive? Yeah, that's right. So speed is decreasing, but positive. Now, in our death example, that would mean that the kid is still gaining altitude. That's what that would mean. If I was driving a car, that means that I just haven't stopped yet. Okay? Still moving forward, just haven't stopped. We'll call that 5. From t equals 3.5, time equals 5. We're still decreasing. We've actually had a negative territory now. So this would kind of like be at the top of the parabola on the death example, right there across the x-axis. Do you get that? And then we start going down. Gravity wind starts pointing out of the ground. Now this is not a death model example because he might bounce when he hits the ground, but he ain't gonna do quite what this is suggesting. Okay. All right. T equals 5 until 6.5. What's happening? Increasing, but we're still moving backwards, right? Kind of weird. Increasing, but we're still moving backwards. Maybe just not backing up as fast. If you're thinking about driving, you might have to back up really, really fast. Speed is still, speed is increasing, but it's still negative. I'm done talking about this and writing it on the board. This little interval here from about 6.5 to 8, constant. We probably stopped. I would say there is no velocity there, wouldn't you? So you're backing up for a while and then you stop and you got to change gears. And then you start going forward, don't you? Let's interpret the velocity there. Not that bad. You know, you can think of it in lots of ways. Driving a car is one of the easiest ways to think about these things. Really, really is. Explains it quite well. What's up next? Acceleration. Hey, you've already talked about this. Is there anything behind this little magical box? Acceleration is simply the derivative of velocity, or the second derivative of a position function, which you more or less already have in your notes. Underneath that is the gravity function. 1/2 gt squared. But that's the function that Newton is quite famous for, and his integration into calculus because of an apple. And you can kind of see where the equations that you've used in the past come from. They come from that gravity function. On Earth, in feet, and in English units, Earth's pull is 32 feet per second per second. So the gravity function is 1/2 32 t squared or 16 t squared. That's something you guys have seen all through Algebra 1. You've seen that negative 16 t squared feet. You also saw this a couple of times whenever I used an equation that was written in metrics. 32 feet is about 9.8 meters per second. So you have that 9.8 and you get the 4.9 t squared. You may not have very good memory, but at some point in time you've done similar equations, but instead of starting off with negative 16 t squared, they've started off with negative 4.9 t squared. I promise you they have. That's where it comes from. It comes from the gravity function. But you don't have to know the gravity function. But that's where it came from. All right, dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height, which for some reason your textbook calls S, 160t minus 16t squared feet after t seconds. How high does the rock go? I'm not going to ask you to do this by hand. You could if you remember opposite B over 2a, but probably don't. Everything can be done by hand, but I would say just plug it into a calculator and see what it looks like. That thing is moving up pretty fast. Probably going to have to play with your window. It's launched out of there. It's fired straight up at 160 feet per second. So I don't think looking up 10 units will cover it. I think I'm just going to guess and say Y max is 40. No, that won't work either. It's 160 feet per second. I guess maybe I ought to do at least 1,000. So I'm changing my Y max to 1,000. Yeah, that more than covered it. I also see the entire path too, which is great. So right up here, the vertex of that parabola is our maximum height. Just go back in time 2 years or a year. Second trace. What do you see under second trace that might give you that maximum height? Maximum. Now the maximum works by giving it a left boundary and a right boundary. So you take your little cursor and you get to the left of where you think it is and you press enter. Then you get to the right of where you think it is and you press enter. You don't have to be accurate at all. You just have to be left and right. That's all that matters. And you press enter a third time for a guess. Your maximum height is 400 feet. The time here is 5 seconds. The calculator uses a technique to do this, and sometimes you'll see some interesting things happen, but 5.000019 is 5 seconds. It's got a rounding error there on X. It always does. But Y is going to be... Does anybody say 5 on the money? No. It's 5 seconds. But it's 400 feet. What is the velocity and speed of the rock when it is 256 feet above the ground on the way up? On the way down? What I want to do is I want to go to my graph, and in Y2 I want to put a 256. Because what I need to know is I need to know the times that this is true. Does everybody understand why I'm putting a 256 in Y2? I need to know when it hits 256 feet. I'm going to go ahead and adjust my window back down to 500 so I have a better picture. I'm pretty sure that the velocities are going to be the same. One of them is going to be positive, one of them is going to be negative because of symmetry. But I'm going to find the times by hitting second trace 5 for intersect. And the intersect feature works, get close, enter, enter, enter. So there's a time at 2 seconds. The other one's probably 6 or 8, probably 8. This problem wasn't meant to be confusing. Enter, enter, enter. There's your 2 times. 2 seconds, 8 seconds. You need that information. Time 1, time 2. Now I do need the derivative of this function in order to put this in and get lost. So I need h prime, or s prime in this case. Was it 160 minus 32t? All right, if I plug a 2 into that thing, I gotta get 96 feet per second. If I plug an 8 into it, times 32 is 256, I get negative. Did I do the first one right? I get the same thing. It's just negative. I get negative 96 feet per second. Why is the second one negative? It's on its way down. It's falling. Why is velocity negative? All right, what is the acceleration of the rock at any time during its flight? Oh, that's different. C says acceleration, doesn't it? So C is the acceleration at any time. How do you find that? We take the derivative of velocity. Now, S prime was our velocity derivative. It was 160 minus 32t. So we're going to find S double prime. What's the derivative of 160 minus 32t? Negative 32. That would actually be in feet per second per second. Acceleration says every second you accelerate this many feet per second. So that's why it's per second per second. Part D was nothing interesting. It was velocity when you hit the ground, right? We already did that with a kid, didn't we? Yeah, let's not do it with a rock. Who cares about the rock? You care about the rock? Did you care about the kid? You did not, did you? And I'm the evil one. You didn't care either. Like a whole bunch of people following Hitler. What? Anything interesting in this one? I don't think so. It does have this one at the bottom. It says use parametric graphing to view the motion of the particle on a horizontal line y equals 2. I haven't talked about parametric graphing with y'all. So if you see anything about parametric, ignore it. Something I cut out. I might talk about it at a later date. But their word for displacement here, like the wording is a little bit different than you're accustomed to. A says find the displacement of the particle during the first 2 seconds. That's just how far it's traveled. Nothing more. That's how far has it traveled. B is average velocity of the particle during the first 4 seconds. Is average velocity a derivative? No. I don't really want to spend a whole lot of time doing this thing, but what you're supposed to do is you're supposed to plug in a 4, or plug a 4 into S of t, and then divide by 4. Because you're finding the average velocity that happened there. So if this thing says that the velocity, or if it says the displacement after 4 seconds is 25 feet, then the average velocity to get you there would be 25 over 4. C is a derivative, because what word do you see? Instantaneous. That's a kick. It's derivative. D is acceleration, second derivative. E is about describing the motion of the particle. At what values of t does the particle change directions? E is worth doing. A particle changes directions when its velocity goes from what? Positive to negative. I understand why you're saying 0. Changes directions when velocity, we're not really saying, velocity goes from positive to negative. Now, this is going to happen on either side of a 0. So that's actually worth doing. All you have to do is you have to take the derivative. I haven't finished it up. Bummer. It's not the greatest to be. We'll start there tomorrow. Maybe I explained too much. Huh? I used to be able to do this in a day. Something's happened. Maybe y'all just need more, so I talk more. We lost a minute. We're a minute shorter than last year. It's not like it's that much shorter. Anyways, we'll continue tomorrow.